Oh, hello everyone. Okay, this video I'm going to introduce yeah, it's strange. Where is it? We'll introduce the going to introduce the work, okay? And last video we said work, heat and light is the expression of energy. Okay, so we start to introduce the first term called work. Heat, I think for this semester, I think we won't have enough time to talk about heat. But heat is very difficult. Heat is very difficult concept. Okay, so in this semester, we just talk about work. Okay, so what's the work? Okay, let's see. Let's read about the description of work. It says, in textbook, it says energy can be transferred to a system when an external force does work on the system. Yeah, it's very academic. It's a very academic expression description, but actually, simply speaking, if you want to add energy into your system or object, you want to add energy into a system or an object, you need to do the work. Okay, so okay, but like I say in last video, it's sometimes you can go to reverse way. Okay, so sometimes your system or your object can release the energy from themselves, and at that time there's this system this object doing the work to the outside. Okay, and here in the physics textbook, especially in general physics textbook, it always talks about adding the energy into a system, and you need to do the work on the system, but it can go to reverse way. Okay, especially when you learn engineering, thermodynamics in the second year, you will know your system can do the work from itself to outside. Okay, and here we always talk about inside. Okay, that's just give you the notice. Okay, and how to calculate the work. I think all you learn is in your high school. Okay, the work is equal to the force times the displacement. Force times displacement. But here we have to notice this. Okay, only the well, notice this in this formula. Oh, where's the pen? Oh, sorry. Oh, well, my pen is not functioning. Why? Okay, let me. Yeah, sorry. I'll just reopen my my pen tool here. Oh, oh, it's not working. Why? Why? Yeah, here it's working, but is this not? Yeah, it's working here. So why it's not working in the slide? Okay. Mm-hmm. Okay, okay. Here he said this is a there's a sub here. Okay, there's a minus x here. So it's fx times delta x. This and delta x is displacement. Oh, this means okay, only force component that is parallel to the displacement direction and does work. Okay, that's the meaning of this equation. How to calculate work? Okay, Fx times displacement. Okay, and Fx means only the force component that is parallel to the displacement of direction does work. Okay, okay, let me show you a very simple example. What does this mean? Okay, so suppose we have a displacement like this. There's a force on object, and your force is this direction, and your delta x is this direction. So okay, so the work is equal to the force is equal to F times the delta x. Okay, that's not easy. Okay. Okay, so let's show another example. If your displacement is like this, okay, but your force direction is like this, okay, your force direction is like this, okay, it's perpendicular to the displacement direction. Your work is 0. Okay, because this force is not parallel. This force is not parallel to the displacement direction. This force is not parallel to the displacement direction. That's why this force does not do work. Okay, so this is a two extreme case. One is the force is parallel to the delta x. Okay, one is force is perpendicular or normal to your delta x. What if something is in middle? For example, if delta x is this direction, but your force is this direction. Okay, and there's an angle theta. So what is the work? Okay, so in this equation says only the force component that is parallel to the displaced direction does work. So what is the force component that is parallel to the displacement direction? In this example, what is the force component that is parallel to the direction? So force is a vector, right? Okay, and force is a vector, so we can decompose the force, right? So vector calculation is really important. So this force vector can be decomposed into the addition of these two vectors, right? Right? Yeah, the vector can be decomposed by the two vectors added together, okay? And this component is called F sine theta. Okay, and this component is so-called F cosine theta. And the component F cosine theta, this component, its direction is parallel to the displacement direction. So this component does work. So it's F cosine theta times delta x. And what about this force F sine theta? Because F sine theta is perpendicular to the displacement direction. So this this force does not do work. Doesn't do work. Okay, so this tell you when you're trying to calculate the work, so you have to be careful the direction of your motion and the direction of your force. Okay, you need to be careful for this. Okay, not just the using force times delta x. Only the force component that is parallel to the displacement direction does work. Okay, be careful. Okay, so next is the unit of work. Okay, work is, like I said, work is the expression of energy. And energy in our textbook or in SI system, we always use the joule as the main unit of energy. So work is a kind of energy. Okay, so the unit of work is also joule. Okay, and from this expression, work equal to force times displacement. So work, okay, is the unit is joule and is equal to force in SI system, or force unit in SI system is Newton. And the displacement in SI MKS system, we love to use the meter. Okay, so joule also equal to Newton times meter. So Newton times meter is joule. Okay, remember this because I found a lot of students doesn't know this relationship. Newton times meter is joule. Yeah, because it's not really intuitive. Okay, so this is something you have to remember this. Okay, so this the very simple description of work from your I believe this is also taught in your high school. Okay, and so the next line is, okay, so we need a more general expression of this formula. We need a more general expression of this formula because in reality or in more complex case, yeah, we need to use vector to express this equation again, because force, like we said, force is a vector, displacement is also a vector. Okay, so when we want to calculate the work, okay, how to use vectors to calculate the work? Okay, I believe this is the next slide. Okay. Oh yeah, before the next slide, okay, that's a vivid expression of the work. Okay, we see the baseball, you see the baseball picture. In baseball picture have to pitch. Okay, want to pitch when he does the pitch, that means he do the work on the baseball. Okay, he do the work on the baseball. Okay, you add energy into the baseball, so the baseball can have the very high velocity as it's released. Okay, that's because the pitcher does the work, add energy into the baseball, so make the baseball has high velocity. And this video is the pitching sequence for the Spencer Strider. He is a really good pitcher, so you can take a take a look at this video, and his pitching sequence is very beautiful, and you feel the power of his pitching sequence. Okay, this slide, yes, this three slide, just what can I say? The direction between your force, or the direction between your force and displacement vector is very important. Yeah, when the force parallel to the displacement direction, so the work is equal to F times delta X. But for the middle example, you are pulling a luggage. Okay, you're pulling a luggage, and your pulling direction, your force direction is not 100% parallel to a displacement direction. Yeah, you're pulling luggage. Your displacement direction is here. Okay, but your force is here. So only the force component, or only this component does the work. Yeah, displacement is here, and the displacement direction here, your force is here. Okay, so only this component does the work. And here, the right example, a waitress or waiter holding a plate, okay, and do the displacement in this way, okay. But this force, the force that the waiter or waitress hold the plate, this force doesn't do work because this force, its direction is going to upward, and it's perpendicular to your displacement direction. So yeah, it has a force to hold the plate, but this force does not do work. Okay, that's very interesting. Yeah, force there to hold the plate, but this force doesn't do work because this force is perpendicular to the displacement direction. Okay, so yeah, so back on the slide. So we say we need to use the more general description expression to express the calculation of work. And here we use a mathematical tool called dot product. Okay, dot product, and I assume you all learned the dot product in the high school. So I don't want to explain it from the very beginning. So when you try to do the work using vector, it's your force vector dot product. This so-called dot product to your displacement vector. Okay, so in high school mathematics, you say the dot product equal to the magnitude of the two vector times together magnitude. This means magnitude. We introduce the magnitude, how to calculate magnitude of vector in chapter 3, right? And it's times cosine theta. Theta is the angle between your force and displacement vector. Okay, so let's see. This is more general expression of calculating work. Okay, let's try it. If your angle, if your force is parallel to a displacement, that means your theta is 0. And this means cosine theta is equal 1. So your work is just equal to the magnitude of force times the magnitude of the displacement. Okay, so that's when your force parallel to the displacement vector. And the other extreme case, let's say, okay, if your force and displacement vector are perpendicular to each other, what that happen? In that situation, your cosine theta is equal to 0. So your work at this situation, this does not do work. Okay. And so let's talk about another very interesting situation. Okay, if your angle between the force and displacement vector are opposite, that means theta is 180 degrees. Your cosine theta is equal to -1, and that means your work is negative force vector times displacement vector, and its magnitude times together. Okay, so this is this situation like this. Yeah, this is like this. Your displacement vector is here, but your force vector is reverse or opposite to a displacement vector. Okay, so you're in that situation, your work is negative, is less than 0. Okay, so let's say so it tell you work can be greater than 0 or smaller than 0. Okay, work can be positive or negative. If a work is positive, that means you are doing positive work. A term called positive work. And if your work is less than 0, that means it's negative work. Negative work. This happens a lot. Yeah, especially friction. Yeah, friction. Yeah, that's a bit friction because friction is always opposite to your moving direction. So your friction always to do the negative work. Okay, because its direction is opposite to the moving direction. That's why friction does the negative works. Okay, we will talk about this later. Okay, so this is the vector description using the vector to calculate the work. Okay, it's not that difficult if you understand how to manipulate the dot product. Okay, what else on the slide? Okay, the next slide is what I say. Yeah, next slide is just what I just said. Okay. Okay, so the final, I think the final part of this video. Okay, I just want to make a small modification on this slide, and it's called a dot b two vector dot product is equal to ab times cosine theta. So I think this should be more accurate, has more accurate description. Actually, this should be, I think you use ab magnitude of magnitude of a vector and magnitude of b vector and times together and times cosine theta. You just use a and b. I think that's not that accurate. Okay, I think you should be better to add this bracket. Okay, that means the magnitude. Okay, so I will the next slide. The next video I will just show you how to use the component language to calculate the dot product of two vectors, and then we'll show a simple example, but that's for the next video. And so I just stop the video here. Okay, stop video, and we will show more example in the next video. So I'll stop here. Thank you for your watching or listening. Okay, I will stop it here. See you next video. Bye bye.